I would ask you, before we talk about what I asked you to do last night, I would ask you to plot this. What does this look like? You don't need to have Q to plot this. You can plot this portion. So grab your TI, grab your phone and bring up Desmos, plot this, put this into your calculator. You don't have to put all of it into your calculator. If you're trying to get an idea of what the shape is, then just make your function something simple that will represent the important parts of this. If you put this into your plotting apparatus, it will give you the shape of this function with whatever, you can put whatever number you want out front. Q is the scaling value here. So if you want your scale to look a certain way, then put something out there. In fact, it might be interesting for you to do a couple of things here, like maybe plot a couple of these, maybe one with e to the negative x over 2. Remember, there's something in the denominator. What is making this number do to your function? Maybe do it a couple of times so you really get an idea for how that can be changed. Maybe make it gregariously bigger and see how that affects the outcome. I think these are good things for you to do. You should already have had an idea for what this looks like. If you don't, then let's do the quick math, right? So all of you are getting an idea now of what it looks like, right? It should be asymptotic. And they all should be, if you didn't put anything out front here, they should all be asymptotic as they approach 1, because you have no scaling value out front. The difference is, I bet between the three of them, some of them take longer to reach 1 than the others do. That's what changing the value under here is doing. It's making it take longer. And now you know what kinds of things you can change to make it take longer, right? If I make R a bigger number, it will take longer for this to reach 1. If I make C a bigger number, it will take longer to reach 1. What is it telling you about this function? Well, I hope it's telling you a couple of things. That if I increase the resistance, it will take longer for the charge to build up on the capacitor. I don't know if that makes sense to you or if it's something that you can rationalize, but because I know I have some people who still maybe haven't put the actual function into their calculator and don't really know what it looks like. But in the future, when I ask for it, because I'm going to, you'll be asked to sketch plots of Q as a function of T. And you'll have to mark things on here that you might know. So maybe we'll say that this is going to be Q, whatever our maximum value is. It's asymptotic. So this is where the asymptote is. And our function's going to look something like that. And as we increase this number, it's going to be taking longer. Does it make sense that as you increase resistance or increase capacitance, it would take longer for your system to charge? Can you rationalize it? Can you, in a sentence or two, tell me why changing the resistance would make it take longer to reach full charge? Think of it. Talk to the person next to you, because I'm going to ask a couple of you why that must be the case.
Less charge over time means more time.
Bless you. When you found the current, you took the derivative of this. Some of you were successful, some of you were less successful. So I'm doing this for the people who were less successful, okay? So I have my function. I tried to do this last night at like 10 o'clock when Sergio asked me, but by then I was tired and I don't think I explained it particularly well. So we're going to take the derivative of this function, right? You can take the derivative of both sides, but I want to point out that ddt of a function for Q gives you the current as a function of time. That's what it's going to produce. The other side of this, of course, is to take ddt of Q times 1 minus e to the negative t over RC. So I know some of you are still kind of new to calculus, still working the ways out of it. So this is going to involve the chain rule. Raise your hand if you have used the chain rule before. Okay, so I have a room full of people who have used the chain rule. Q is a constant. It's going to pass through this derivative. So I'm going to have the Q out here and recognize that I have d dt of 1, because I can distribute the derivative, minus d dt of e to the negative t over rc. Is that okay? You guys see kind of what I'm doing here? Q stays here. The derivative of 1 with respect to time is a constant, so that's 0. The derivative of the exponential is just the exponential function. So the first thing that happens is I get that exponential function back. But the chain rule requires that I now take the derivative of whatever there was inside the exponent. That's how the chain rule works, correct? When I first learned the chain rule, some people believe that somehow I just was born with knowledge. That's not true. I was sometimes just as big an idiot as you guys and made silly mistakes. You are not idiots. I didn't mean to say it that way, but I recorded it, so I had to throw an apology in there just to act like I care. I thought you had to keep doing this until you got to 0, right? Because if you do keep doing this, you will eventually get to 0. The next derivative of whatever's inside it made no sense. But sometimes you pay not great attention in class, and you take that home and you start doing your homework. I'm like, why are all of my answers 0? And you learn that you were doing it wrong. That's how I had to learn. So we make silly mistakes. All of us do it. I figured out pretty quick when the answers in the back of the book weren't 0 that I probably need to go back and check my notes, or heaven forbid, I had to read the chapter. I know that's heartbreaking for some of us, but that's what I ended up doing, reading the chapter. I didn't take calculus until college. They didn't offer it at my high school. So when I take the derivative of this, do you all agree that we get negative 1 over RC? So I now have minus e to the negative t over RC times negative 1 over RC. And I don't keep taking the derivative. I stop right there. All right, so we're done. Sorry, there's a problem. Let's just do that. There we go. That's what I meant to do. So we can clean this up. All agreed? When I clean this up, the negative and the negative cancel, correct? And I get Q over RC e to the negative t over RC. And I know I told some of you that yours was wrong because you didn't have a negative sign out front. I'm thinking about what we're doing today, not what we did yesterday. And what we're going to do today, we'll have a negative sign in the answer. So I'm sorry, that's my mistake. This is the correct answer, kind of. It's correct in that everything is in the right place. This is the result of taking the derivative with respect to time of your charge function. But is this a current? Some of you saw in here Q over C and immediately recognized that you could write this as V over R, e to the negative t over RC. That was a good pickup, and I'm glad that you did that, because it makes the next part easy. This is Ohm's law as well, right? V over R is current. It's not a bad idea to recognize that that is a current, and you could also write this as I max, that in the case of your circuit, you have a decaying current function. I'll leave both of those here for just a minute, because V and R are actual physical constants of the circuit. It's better to express it like this than it is to have it expressed as Q over RC, because Q is a value based on the amount of charge built up in a circuit, but V is actually a physical presence in the circuit. So either of these is fine, I think, but I don't think it's great to leave it in this term, right? Because you have an expression for Q. Now, does this match with what we said about capacitors when I was just giving you kind of the overview? Remember, the thing we said about capacitors is that capacitors have, they act like a resistor in certain circumstances. In fact, we said when they're uncharged, a capacitor has 0 resistance. And when they're fully charged, that's uncharged. And when they're fully charged, the resistor has infinite resistance. I think in our single loop circuit, and I'll draw it again, the current tells this story probably better than the charge does. Right here, if I put, because this is the current through the entire circuit, right? Because all the elements in this circuit experience the same current, even though the capacitor is not passing charge. From here to here, it appears as though current's passing through the capacitor, because I have charge passing out this way and charge passing in this way. Correct? So it appears as though it's passing charge, even though it's not. So in that circuit, at t equals 0, so I of 0, we get I max e to the negative 0. What is e to the negative 0? 1. So we get the full amount of current possible, V over R. It's like the capacitor isn't even there. We know that this is the result of V over R. We have it proved right here. I'd say this is the evidence that a capacitor appears to have 0 resistance when uncharged. We know it's uncharged because if we go back to our original function way over here, what is the charge in our system at time 0? Well, let's put it in. Q of 0 equals Q times 1 minus e to the 0. What is e to the 0? 1. 1 minus 1 is? So this is 0. No charge at time equals 0. Good? So we have all the parameters are working out for us. So I come back to, let's consider the other parameter now, right? The other parameter is when the circuit has been closed for a long amount of time. So let's get rid of all that and consider the other extreme. The other extreme is at t equals infinity, which, by the way, infinity is not particularly long. All right, it's right over there. So I at infinity just means after a very long time equals I max e to the negative infinity. You've had calculus. E to the negative infinity is what? 0. There's no current in the circuit at infinity. But again, infinity is not a particularly long time, right? Not a particularly long time. Over here, we switch this up, right? We change that to be infinity, which means that this is going to be negative infinity. And that's going to be e to negative infinity is 0. 1 minus 0 is 1, so this will just be q. No surprise there? All right. So we have what's, actually, I'll just go to a new page. For a simple RC circuit, we have proven the concept that capacitors behave as though they are a transitional resistance in the circuit, starting with a resistance of 0 when they're uncharged and ending with an infinite resistance when fully charged. Now, this will be true in any circuit containing a capacitor, even if it's not just a single loop circuit. If you have a capacitor in any circuit, no matter where it is, when it's uncharged, you treat it as though it has 0 resistance. And when it's fully charged, you treat it like it has infinite resistance. The last page of your homework, that's what that is about. Looking at the steady state versus the initial state. So to make it easier, just make a new circuit if you have to. Draw a new circuit with the capacitor gone and no resistor there when it's at time 0, and just open up that circuit. That whole portion of the circuit where the capacitor is has infinite resistance. It's like a switch is open. So replace the capacitor with an open switch there. All right? That's how you can kind of use this idea that the capacitance acts like a resistance. We have a charging function, and it is not on the equation sheet because you can prove it. But you saw what it takes to prove it, right? Again, things to memorize. This might be worth it. You'll never be asked to use it without having proven it first. But do you have time on the multiple choice to prove it? Yeah. So it's not particularly hard to memorize. Before we leave this, though, what would happen to this if we divided both sides by C? Do you know what I'm getting at here? This would be voltage, right? This would be the voltage across the capacitor as a function of time. That's exactly right, which would be the voltage of your circuit. So just like that, it mimics the charge. So if we divide both sides by C, we get the voltage across the capacitor. Now we also have, in this case, the current as a function of T, which ended up being I max e to the negative T over RC, or V over R e to the negative T over RC. I'll say this too, if I multiply both sides of this times resistance, do you see what you get? The left side's got to be the voltage across the resistor, which will have to be the voltage of the circuit, e to the negative T over RC. So getting rid of my Q's there. You only really need this one because everything else is derived from the charging circuit, from the charging function, but you understand that these are the results. Now, this is for a resistor capacitor series. All right, these reflect what happens in a resistor capacitor series. So when you have that set, we have voltage in one, starting at 0, and the other one starting at max, and they change places. Isn't that what the bulb did? Connected this circuit up. The moment we flicked the switch, bulb got all the voltage, all the current. Then over time, the bulb got shut out. It wasn't just because current was dropping. The voltage across the bulb was also dropping at the same time as that voltage built up on the capacitor. So we wait a very long time, and we decide to take this circuit and isolate the charged capacitor. Putting a little asterisk on there to tell us that I isolated this circuit after the capacitor was charged. So it is a fully charged capacitor, and it has the voltage of the original battery from earlier. We could build a bit of a new circuit and reset T equals 0 to be the moment we close this switch. Is it clear to you guys that the moment we close this switch, we're going to have a flow of current? So, hear me out. We took this right off the original circuit, and the original circuit kind of looked like this. Remember the original circuit was here? That tells me that this is the positive plate and this is the negative plate. Right? Because that's how it would have been charged. Because this is the positive side of the battery, and this is the negative side of the battery. So I open this switch, and then at time 0, I close the other switch. This is a discharging circuit. It will discharge the energy from the capacitor. I'm going to write this down because I think it's appropriate. You may think that because the capacitor is charged, that we would write it without the negative sign because it has energy in it. But a capacitor is not an active device. It is not continuously providing a potential difference. So we still write it as a voltage drop across the capacitor. This capacitor at Q equals 0 is fully charged, right? So we're going to start with this. This is where we're going to go on Monday.